Welcome back, ladies and gentlemen. This is video 4, and we are going to do question number 25 to 28, which involves logs and exponents. These are a couple of principles you need to know about logs, a couple simple identities. I'm pretty sure you know them all. Uh, if you're watching this video about Thomas calculus, I'm pretty sure you know all of these. I just mentioned them here just in case they come up. These are some other identities, they come in handy, especially the last one while solving limits. This reminded me of one more formula of log because I didn't mention it here. It's another very simple elementary law of logs about the powers of logs, how you can multiply the log of something with the power of the subject your log of your logarithm, right? I wrote ln x here. It can be any other log with any other base. Ln is the log with the base exponent, like Euler's constant is the base of ln x. The graph of ln x, or any log x actually, in fact, is symmetrical and a mirror of the graph of an exponent function along the line y equals to x. You all know that probably. The graph of ln x actually like becomes asymptotical. I don't know what how what as you to call it, to minus y, to like the y-axis, but it goes towards minus infinity as you are reaching x equals to 0 from the positive side. There is no negative x values on the graph of ln x or like log x in general, unless you have some plus minus in there. The function inside the log should not be the function. I should have wrote h of x or like f of x should not be less than 0, or the graph is just undefined. You have nothing here. It is because you cannot raise a negative value to like make a consistent continuous graph. Like for a positive value you can raise it to 0.5, but for a negative value you simply cannot do that, right? And like you can just open Desmos right now and try and graph y is equals to minus 2 raised to the power x. Minus 2 should be in bracket, or like Desmos would automatically identify it as minus bracket 2 raised to the power x and then bracket close, so the minus will just automatically go out. Like I wrote this here, the function, like I wrote this, like just try and graph this on Desmos. It won't show anything because it's not a continuous function. Imagine this: you raise minus to the power 1, you get minus 2. You raise minus to the power 2, you get plus 4. You raise minus to the power 3, you get minus 8. Like it's just 2 minus 2 plus 4 minus 8. It's not continuous simply. And like how do you reckon you can possibly uh, raise minus 2 to the power something like minus 2 raised to the power 0.693 or something like that? It's just not possible. There are basic set principles on how you raise the power of plus 2 to 0.693, right? And it's not like unknown that you cannot raise the power of a negative number. You cannot raise the power of negative number to 0.5, because then you would get iota and enter the complex plane, right? So basically it is it gets complex, right? You need to study some other math for that. We are not going to discuss that here. The graph is simply not continuous, like I mentioned earlier, right? So yeah, that is the obvious part of all of this. uh, hmm. Yeah, I just kind of like taunted at you guys here. This is a voiceover, by the way. Like if you haven't realized yet, my microphone wasn't working and my video recorder was messing with me a lot. Like it messed with me afterwards. Even like by the end of the video, it did mess with me, which kind of angered me, pissed me off. But whatever. Yeah. So just yeah, I came back here just to mention that the only root of any log function is one. Of a log function with x in as a subject is 1. If it's hx, then it would be 1 only when wait okay, yeah, it would be only when hx equals to 1, right? The graph of log with a subject hx would only be 0 when hx equals 1, right? That would be its only root. Yeah, so we come back to question number 25 here. Question number 25. What am I doing here? Yeah, I'm just highlighting what I wrote there. Yeah, it's obvious stuff. X raised to the power 0 is 1. In fact, 0 raised to the power 0 is also 1. It's proven. You can see Thomas Calculus advanced question for that. Thomas Calculus is advanced exercise for chapter 2. Okay, so yeah, no graph on the negative x-axis values. On the negative x-axis, there is no graph, right? On the positive x-axis values, as you approach 0, as you go nearer and nearer to 0, you approach minus infinity, which is basically you are asymptotic to the y-axis and approaching negative infinity, right? You never touch the y-axis, right? So yeah, this question just involves that part. Ln0 is undefined because again the limits from both ends does not match, right? Limit from ln x when x is approaching 0 from the negative side is undefined, and ln x when x is approaching 0 from the positive side is minus infinity, right? So it just becomes undefined because it's not continuous. Discontinuity is basically an undefined value, right? So to put it simply, we can say limit h is approaching 0. We can just like use a x example when I said x is approaching 0 from the positive, h is approaching 0 from the negative. But the h is actually a function of t, where ht is equals to t minus 3. It's just a notational trick I did to like simplify what I'm trying to tell you right now, right here, just to clear things up, not make it too messy. I would never do this when I'm solving it for myself, by the way. Yeah. So h is approaching 0 from the positive end because they mentioned that t is approaching 3 from the positive side, right? So h is approaching 0 from the positive end, right? Because it was a positive linear graph. So back to question 26. I wrote question 26 here. Mm-hmm. Yeah, so this question you just need to put in the limit and just it solves itself. Like you do not need to do anything else. You just put in the limit and just automatically solves. Uh, Always try to put in the limit values first and figure out what's the problem with them. If it's like the denominator is getting becoming 0 or something along those lines, you got to do something else. If it's like there are many other things, right? If it's I don't remember, if it's like infinity divided by infinity, you do something else. So you just put in the limit and it just automatically solves here. Again with the log 0 log 1 equals to 0, again with that formula, because x raised to the power 0, any x raised to the power 0 equals to 1. So it just solves automatically. Pretty easy question. Back to question 27. Looks really hard is very easy. Looks really hard is very easy. I'm saying it again. It looks very hard is really easy. Right? You're like, oh my god, under root theta multiplied by exponent of cos pi upon theta. Why did they have to like put pi in there? Oh my god, that's so hard. No, it's actually very easy, right? So basically, like, cos theta, any theta inside cos, whenever you any theta, like how, no matter how big, cos will always oscillate between -1 and 1, right? The cos will never get out of its way. Like cos will never be -2 or -3. Cos will always be -1, minus between -1 and +1. It can be 0 and something like that. I didn't add a d to the and, but like just forgive me for once, right? Cut me some slack. Okay, so minus 3 where theta is approaching 0. Theta is positive, like theta is approaching 0 from the positive end and very close to 0, right? So it can be 0.00 plus 0.00000006, something like that, right? So the my under root theta just becomes 0 at that point because like theta is very close. If we were approaching from the negative end of the theta axis, then under root theta would not be 0. Under root theta would be impossible to do and would enter the imaginary plane because you cannot take under root of negative values, right? So theta is approaching 0 from the positive end. You just do under root 0 multiplied by cos infinity because it was pi upon theta. Theta is 0. Cos infinity oscillates between 1. 1 and minus 1. So we put the two extreme ends here. Cos can be minus 1 or cos can be plus 1. 0 multiplied by e plus e raised to the power plus 1, e raised to the power minus 1 does not matter. Both are going to be 0 because anything multiplied by 0 is 0, right? That's the basic principle. So it was a very easy question. You did not need to think that much. Pretty simple, pretty easy. That's how you usually go with exponential questions, except for the ones that actually like need derivation, where you have some kind of fraction and you make it into like a something like e raised to the power ln of that fraction, and then you solve the power of exponent, something like that. It's like classic exponent stuff, right? Question 28 involves 2 exponent 1 upon z upon e exponent 1 upon z minus 1, where z is approaching 0 from the positive end. That is an important factor because like 1 upon z is undefined at z equals to 0, because like from the left hand side you're approaching negative infinity, from the right hand side you're approaching positive infinity. So like, you're not approaching either positive infinity or negative infinity at z equals to 0, so it's undefined there, right? So yeah, just put in the value of infinity. Plus infinity, it doesn't work, so like you try some other way, you try to rationalize it. As you can see, there's a e raised to the power 1 upon z on the numerator, and there's a e raised to the power 1 upon z on the denominator. You need to somehow cancel these so that the denominator and the numerator become something else than simply infinity upon infinity, right? You need something else other than infinity upon infinity, because exponent infinity is obviously infinity, right? So you're raising exponent, you're raising zero, you're raising like what's 2.3 something to infinity, you get infinity. If you were raising something like 0.9 to infinity, you would get zero, right? I'm pretty sure that something below 1 raised to the power of infinity just approaches 0 straight up. Yeah. As you can see, exponential function, you obviously know the exponential function, the gradient keeps simply increasing and the exponential function just goes up. So will a linear function actually. If you just account for x approaching infinity, a linear function will also approach infinity if it has a positive gradient. E minus infinity is 0, because minus infinity would render 1 upon exponent infinity. 1 upon exponent infinity equals 1 upon infinity. Does not necessarily equal, but like infinity is just a term used for a really, really, really big and like endless, unaccountable for a number. So like e minus infinity is just 1 upon e infinity, which is 1 upon e infinity, which is simply 0. So I took e 1 upon z common from the denominator, which gives me 1 minus 1 upon e 1 upon z. Really mouthful to say, a really mouthful thing to say, but yeah, the limit is z is approaching 0. So here what happened was basically my video recorders, my screen recorders stopped working completely. So it's like very basic maths after this. Sorry, pardon my marker size. So you just cancel the e exponent 1 upon z from both the denominator and the numerator, right? And like look, in the denominator you have 1 minus 1 upon e raised to the power 1 upon z. 1 upon z is infinity, right? And you are getting 1 upon e 1 upon z. So 1 upon e infinity. E infinity is infinity, like I said, right? So e infinity is infinity, and you are dividing 1 by infinity. 1 divided by infinity is simply 0. That is what 1 upon e 1 upon z shows. That is really a mouthful. I do not know how you are not confused by that. If like, how you wouldn't be confused by that. So we get this value and we just put in the limit. Z is approaching from the positive x-axis, so it's plus infinity. And like if it was approaching from the y-axis, then it would be just infinity on the numerator. If you can make sense of that. Yeah, just putting in the limit gives us the answer. These questions weren't that hard. I actually started this playlist because the initial starting questions were hard. 17 and 18 seemed hard to me because like they were introducing a new concept when you begin to use rationalization. You cannot even use rationalization on question 18. Like, cut me some slack here, right? I will make more videos on from Thomas, probably some advanced from the advanced questions videos, if you wanna stick along. All right, tada, bye bye.